All right.
Okay. Hello, everyone. Welcome to the panel session for this first section of Maine on memory. Technically, this is a panel discussion on memory in brains and machines, which is a topic very dear to the heart of everyone here. You likely all know all the speakers who you've just seen. Kareem, Ida, and Nicole. And also, in case you were unaware, we have with us Tim Behrens, who was the senior author on the work that we saw presented by James Whittington earlier. So I'm going to start by just asking a couple of broad questions to get discussion going. But to the audience, please go ahead and ask questions. And questions that get upvoted a lot, I will ask of the panelists. So to get us started here, I want to ask a question that came up actually during the learning salon that I did, which Ida helped to organize, which was a great question from the panel, from the audience in the learning salon. And that is, what is the difference between, let's be specific here perhaps, episodic memory and knowledge? Is there one? And if so, what is the relationship between the two? So anyone who wants to go ahead and jump in, but alternatively, I can ask each of you in turn to give your thoughts on this.
I think, aren't you the most qualified person to answer that question, Blake?
I'm not a panelist here. I'm sorry, Tim. This is on you.
I feel like you worked directly on that question.
No, but I mean, this came up, for example, in James's model. It comes up in Ida's work. It comes up in a lot of questions, and it's very relevant for AI. You know, when we're thinking about building these systems, I guess this is partially an engineering question. Do we have to have a separate memory module and knowledge module, as it were? Or like, you know, what exactly are we talking about when we're talking about memory? What for you distinguishes a memory per se, as opposed to just knowledge about the world? Do you want to give it a go, Ida? What's your thoughts? What are your thoughts?
Yeah, so that's a great question. First of all, great to be in this panel with so many wonderful people. It's the most junior member of the panel. Happy to go first. So something that I think is very interesting in this question is the knowledge that doesn't need to have been experienced by me. I could have learned it from the experiences of other agents or from the culmination of experiences of many agents that might have gathered that knowledge together. But it could have been also figured out by myself. However, it's in the form of, I know that X, so to speak. It doesn't need to be in the form of, I experienced X from a first person perspective, where I remember the experience X. And I think that that's an important distinction, that for our models, what it ends up being, for models that are not multi-agent, for models that are not learning in either by imitation learning or by some other kind of acquiring knowledge from others, is that experience has to turn into something else. So it's in this format that's not experience dependent. So for instance, finding out that, I don't know, like Paris is the capital of France is a favorite sort of example that a lot of people give for these kinds of things, or that dog is a kind of mammal, or these kinds of things. There's not one particular episode in my life that helped me, or that you know, uncle is the brother of a father, or the brother of a mother. These kinds of things you don't rely on one specific experience per se. But I think it gets very close to theories of categorization, where you have this kind of central idea versus particular samples that you might be remembering, or an average of them. So we're not entirely sure how that process happens. There are a certain number of theories, some of which might be related to these kinds of multi-step abstraction of associations that one has learned, and maybe some kind of a basis set thereof, or some kind of a eigen decomposition thereof, some kind of a clustering of experience from different kind of dimensions. So there are different kinds of models that could address how experience turns into that kind of a semantic knowledge. But I think it's a very interesting area of work, both for computational purposes and for ML. In ML in particular, I think some work like neural Turing machine and other work that have tried in the past to have some kind of an external memory that's independent of just the experiences have had a particular issue of their order of sort of the order of the memory was not, let's say, efficient enough. So it was a order n. So for every memory, you had something stored in those slot-based sort of ideas. And I think very interesting approach for the future of these kinds of external memories for AI and ML is that they would be of log n order. So you could store less than the actual experience. And I think that's something that in order to bring these two together, these kinds of compression and efficient storage of memories, especially new memories, might be a way to go.
Cool. Great. Thank you. Does anyone want to add to that, or should I move on to the next question?
I mean, I thought that captured a lot of the things that you might say. So I think that a classic distinction that Ida mentioned was the difference between, and that you've worked on, Blake, is the difference between a sample of the world, a particular experience of the world, and the statistics of those experiences, which make up knowledge. I think that that's very important because your cortex is figuring out how all of your experience, trying to extract the relevant part of how all of your experiences work in order to provide a framework for every particular experience. One other thing that I think is worth thinking about in this context is just how different your brain is from a convolutional neural network in how those experiences are put together. And so in your brain, there are particular brain regions that are modular, that code the different parts of the experience. The schema of being in a restaurant and the face of the person who you're next to are coded in very different parts of the brain. It's difficult to imagine how you could put those things together into an experience when one of them's here and another one's here, unless you had something like a hippocampus, which gets inputs from all of those regions and has this very distributed connectivity. And so I think that that's something that's really worth thinking that's different. In some cases, in some sense, it's not just doing memory, but instead it's taking a bunch of what we would call factorized representations. So my face can be anywhere and the restaurant can be anywhere separately, and putting them together into a whole representation, and then organizing how it plays out that experience so it can go and build new representations in cortex. And all of that, I think, is really important, things that are done by that system that are sort of at the side of what we might think of as memory.
Mm-hmm. Great, thank you. Okay, so another question that I wanted to ask the panel, because I think there were some, again, certain themes that popped up again and again, and for me, I see them popping up throughout the literature, so there's potentially a convergence here that I want to ask about. We see more and more, I'd say, implications of prediction errors and kind of surprise signals in the question of what gets stored in memory, what gets retrieved from memory, etc. And I want to know, this is a very speculative question, but do you think that we are moving towards a sort of unification of, as it were, unsupervised learning theories, which often rely on questions of prediction error and how well your existing model matches the data that you receive, with theories of episodic memory? And are we going to see a sort of like fully integrated prediction module that incorporates both perception and memory into the stack of prediction errors?
Who are you talking? But you're going to answer.
Yeah. So again, like I said, you could jump in, but if you don't have, if you guys aren't feeling aggressive like that, let me start by directing this to Kareem.
Yes. So I mean, I think that you're right. I think there is a move towards integrating those two separate lines of inquiry. I think our take on it is, your brain, I think the general principle that your brain is generating these internal models of the world that it's always comparing the outside world to is a good principle. I think we've always thought of that, as Tim mentioned, in terms of thinking about the statistics of the world, and those statistics of the world give us these predictions and these expectations. But I would argue that if that's a good principle, then it should extend really to even episodes or events that we experience. And I think that's what we tried to show in the study that I talked about in my presentation. But the idea is that, your memories over time and your experiences do contribute to both knowledge, but also to expectations, to these models of how the world should work. And that could happen after a single memory. It could happen after reading about, sort of, let's say, about cheetahs over and over again. Whatever it is, it's going to generate this expectation for the world. And that ultimately will be used by you to actually compare the real world that you're experiencing to those expectations, generate those prediction errors. So I would argue that, I think what you said is absolutely correct. There should be this integration of the two lines.
Great, thanks. Nicole, do you have any thoughts on that matter?
I don't know if I have anything incredibly profound. I mean, I would start with the observation that there's a timescales question, right? And so as we go up deeper and deeper into the hierarchy, so even the retina can remember and predict, right? And the retina can actually do some really cool predictive computation, as our retinal friends have demonstrated to us. But they can only do it on very short timescales. And so as we ascend the system, what we find is that memory lasts longer and prediction lasts longer, right? And those two go hand in hand, we know theoretically. And I guess the interesting question for me is, at what point is this not just a hierarchy of timescales, that you're adding more of the same at longer times? And at what point do we actually see a fundamentally different computation, right? Coupled with the observation that the hippocampus is a really distinct structure. The hippocampus is not a cortical unit, right? It's a different beast. And so I think the interesting question is, what is it doing that's unique and different than just remembering things for longer and predicting things along longer timescales? Like, what is it fundamentally doing different? That's what's interesting, I think, to me. That's how to pose the question.
I actually think this is a great question, so I want to build on this, if I may. Indeed, like, what is the difference between the hippocampus and, say, just the very top of your hierarchical predictive model, right? Like, why is it a different circuit structure? What is it doing differently from simply providing you with the most abstract, high-level, temporally extended set of predictions? Anyone's welcome to jump in. Ida, do you have any thoughts on that?
I just want to say, Tim and I had a chat about this at some point, difference between prefrontal cortex and hippocampus in terms of the hierarchies of predictive representations.
Yes, this is good.
So I would want to hear first Tim before I, if he has something.
Okay, Tim, what are your thoughts on that? How is the hippocampus distinct from simply the top of a hierarchical predictive model?
I agree with Nicole that it's a very, very different structure, and I agree that we need to think about it computationally differently, and so somehow the things that, when I think about hippocampus about it being different from cortex at all, I think about the fact that that neurons get inputs all the way along the long axis of the hippocampus, not just from their local friends. And I think about the fact that there's this very regular input structure from the medial and lateral entorhinal cortex, and those synapses are getting these neuromodulatory changes for attention or exciting events that allow them to label, tag memorable events. And so I think that's why I'm attracted to this idea that it can temporarily, at least, store an index of the whole cortex, because it can tie together things coming from very disparate parts of cortex along its long axis, right? Because the back of the hippocampus is coding sensory stuff, and the front of the hippocampus is coding emotional valence, that kind of stuff. But it can tie them all together, and then back and front is top and bottom for rodent people, and it can label the important ones with dopamine, with norepinephrine, and it can and then it can the connectivity structure into the hippocampus has to be such that it can then reinstate those things into cortex to reactivate the experience, just like Kareem told you. That's a really specialist thing. Cortex, like, let's assume badly that cortex is really just clustering stuff, and it's clustering stuff in time or in sensory. Like, that isn't what I just described there for hippocampus. It's a really different type of computation, and so that's how I see it, definitely. And so I think that the fact that you sometimes see similar types of activity in hippocampus and cortex is because it happens to be that the cortical region that is being reinstated right then, or the input to hippocampus right then for that memory, is from that particular cortical region. You can often see visual cortex co-activating with hippocampus, or Ida can see prefrontal cortex co-activating with hippocampus, right? It depends on where the input's coming from. That's my take. I'll stop now.
So, given what Tim has said, Ida, what's your take then?
So I don't think all cortical regions are born equal or raised equal. I'm I guess a prefrontal cortex specialist, not in the sense that I'm the specialist, but I think it's special. But at the same time, I agree with Tim that the hippocampus has something special going on as well. I think what we learned from especially works like Anna Shapiro's and others is that there's something about there's something about the hippocampus that enables rapid statistical inference that the cortex might be able to do, especially the prefrontal cortex might be able to do, but it just needs more time. And we see that in patients, for instance, who have hippocampal damage, they can learn some statistical learning tasks, but just slower. But also we know that some forms of damage, and we're not sure whether, for instance, in case of HM, what else exactly might, because there was like a larger damage. We know that it might impair learning of new maps, for instance, if you don't have a hippocampus. So I think that's what makes it very special. If you lose some chunks of your prefrontal cortex, that everyone says, oh, we also observe place cells here or this other location. But if you lose those regions, you don't lose your ability to learn a new map. But if you lose the hippocampus, it turns out you do lose that. So I think we still don't know why there isn't another sort of brain region that can help, let's say, HM learn a new map the way that the hippocampus could do, or the medial temporal lobe, whatever it was lost in him, could do. And so that I think our computational models will still have to capture, because as Tim was saying, we have a lot of similar models for different parts currently, and maybe we should do a better job of having the hippocampus part of the model be able to reinstate some of these patterns that we are observing also elsewhere. So I think that's important. And I'll stop there and not go into the PFC. I just want to say it's special.
Fair enough. Okay, there's one question from the audience that's been upvoted a lot, so I'll turn to this now for a moment. What are the this is from Guillaume Lajoie. What are the dynamic ways other brain areas query memory areas of the brain? How is the request for information rooted, and any thoughts on how this is implemented? I mean, again, this could go to a variety of people. Maybe Kareem, we'll start with you on that question.
Sure. Can you hear me? Because I got kicked out. And
yeah, we can hear you.
Great. So I don't know if I would sort of say that there are these different necessarily. I wouldn't necessarily say there are these different modules in the brain where one is querying others to sort of evoke or to try to retrieve memories. I would say that the whole system kind of works in an integrated manner, such that if you are given a cue, or if you have even an internal cue or an internal sort of thought that cues a pattern of activity, that's enough to retrieve a particular pattern that you are trying to retrieve or trying to remember. So I feel kind of my thoughts are very similar, very aligned with what Tim was saying in terms of different brain regions containing, representing different pieces of information, but this information being integrated together across these different brain regions. And ultimately, when you retrieve a memory or an experience, what you're doing is you are actually reinstating these patterns that involve the different brain regions that represent the different pieces of information that comprise that memory. But I wouldn't argue that there's like a little thing in there that's actually doing the querying. I think you're essentially completing these patterns.
But to play devil's advocate for a moment, let me just put this forward. So like I can actively try to recall an image I've seen versus actively trying to recall some audio signal I've heard.
Yeah.
And I don't necessarily, as Tim mentioned, the hippocampus is connected to all of the cortex. And when I recall a memory, it's not that everything comes flooding back to me. I can selectively request, as it were, particular parts of memory.
So I think that's a very good point. And the question of memory search is certainly one that we don't fully understand. Like, how is it that you actually can actively recall a particular memory or a particular sound or a particular scene? But I would argue still, though, that if for whatever reason you have decided internally that you are trying to activate or reactivate this particular sound, that is generating a cue in the patterns of activity that are accessing or promoting pattern completion in those areas of, let's say, auditory cortex or where sounds are represented. Now, how that actually gets initiated, I don't know, but I don't think anyone really knows. But
Nicole, is there any data on this out of curiosity? Like if I try to recall a specific image, do we know something about the difference in activity patterns that occurs versus when I'm just engaged in episodic recall more generally?
I don't know of any data. I mean, the thoughts that come to mind are, that so much of memory mimics perception, right? So the cortex, the hippocampus is kind of tickling the cortex to do what it normally does when it's perceiving. And certainly we can attend to things differentially, right? So we can attend to sounds versus vision. So I would be surprised if those same mechanisms aren't exploited in this process, but I'm not an expert in the field.
I agree with Nicole. It reinstates the thing, and then you attend to the bit you want.
I see. So that's interesting. So the answer then to Guillaume's question is you reinstate everything, but you attend to specific components of it.
Well, I mean, but attention also. So hippocampus tries to reinstate everything, but it interacts with attention, and so the attention, the bit that gets reinstated is the bit you're attending to.
Do you think there's no attention signal within the hippocampus though? Like, can the hippocampus be asked, as it were, to attend to specific components of the episodic memory?
Don't know the answer to that question. I do think that you can definitely what you're attending to at the moment of encoding definitely has a massive effect on what's remembered, and what goes into hippocampus. But I don't know whether you can selectively ask it. I doubt actually, because the hippocampal representations are so conjunctive, I want to call them. Like they have everything about the experience built in, that I very much doubt that you could do that, but I don't know the data on it.
Do you want to add to that, Ida?
Yeah, I think I might go a little against the grain right now, because first of all, patients who don't have hippocampus can recall things selectively. It's not that the hippocampus is necessary for being able to actively recall something that happened before, for instance, the loss. And secondly,
there's a big debate about whether they can, right? Because I'm happy to accept that, but there's a big debate about whether people without hippocampus are really recalling the episode or recalling the semantics.
Yeah, that's right. So I fully agree with that. So if I go back to Guillaume's question, it says memories. So I'm just going to, if that's just like, that challenge between whether what's patients without hippocampus are remembering is memory, or that episodic or semantic sort of consolidated version of that memory. I think, because we know that the autobiographical memory also has cortical consolidation elements to it. It's not necessarily the case that you lose everything that's episodic with the hippocampus. But there are studies, for instance, the Anderson lab and the descendants of the Anderson lab in Cambridge over the years have worked on active recall and active forgetting. Various groups that have sort of grown out of the very fruitful tree of the Schachter lab at Harvard have, including sort of Ken Norman, who I trained with at Princeton, have done work on sort of these sorts of work, and Mike Kahana's lab at Penn has done work on this. I think that there is a role in prefrontal cortex in active recall. I also don't think that everything comes up at once. So on that, I'm going to disagree with Tim a little bit. I do think that this idea that existed since the 70s, that recently with Bo Sivers, we had a simulation model of it, spreading activation does make sense. So internally, my prefrontal cortex can drop sort of a kind of internal activation signal somewhere, and from there it can sort of spread around until the search can lead somewhere. So I think when we want to remember something, probably we activate the closest thing that's accessible, and then we move around from there to find the actual memory. And so I don't know. I don't think everything comes up at once. I do think that the selectivity is kind of top down, at least in humans. So.
Cool, thanks. There's more audience questions that I want to get to here, but I want to first get to a question that was raised during one of the talks. I think it was actually during James's talk, and which didn't get attended to, pun intended. And that is the question of, do we need to capture causal relationships in episodic memory structures? Or like, does the brain do that? And if we're going to build an AI with episodic memory structures, should we also build that in there? Or is the brain merely capturing correlational relationships, and that's going to be sufficient for our systems as well?
Are you allowing, when you talk about causal relationships, are you thinking selectively about intervention models and counterfactuals, or
yes,
or are you allowing temporal understandings of cause? Because I think that these systems are really good at predicting in time, and you can extract things that look like causality from time, right? Because it's not just correlations of things that happen at the same time, right? It's things happen before each other.
Yeah.
However, like if you're asking whether these things have low-level intervention, like do algebra going on, then I just don't know where to start answering that question.
I mean, that was the question, because let's say we take it for granted that the hippocampus has an understanding of temporal relationships. So A occurred before B. And this, of course, is part of the causation story. But the question, I think, is more beyond A occurred before B, do you have do calculus relationships embedded in there? Not only that A occurred before B, but that A caused B, and C, which also occurred before B, did not cause B.
Someone else should take that.
Okay, is there anyone else who wants to weigh in?
So don't you think that your understanding of causality is going to be based on what you've learned over experience? You know, if over experience you've learned that A before B generally means that A caused B, then in any new experience, when you see that A happened before B, you're likely to map that pre-existing structure onto this particular episode.
Yeah, I totally agree with that. I totally agree that we're very likely to learn something that's a bit like it. Some of these representations, these structural representations, akin to what James has been doing, can learn what things are likely to be causal. They definitely can, and that is definitely part of your representation. But the little bits and pieces of the neurons together, there was no do algebra in there. They're just learning the statistics of what comes before each other on average in the world. And it's not just in this data set, it's on average in the world. So those you can get a very rich understanding that might be very correlated with causality there. I'm sure that is happening. But I don't know about whether the nitty-gritty of the circuit cares about the kinds of things that Blake was asking about.
I want to sort of, I guess I'll second that. And the way you were describing it, Kareem, you were saying there is a template of causality matched to this experience that I just had. That template is not episodic itself. That's a semantic.
No, correct. Yeah, exactly.
Right. That's knowledge that you learn from, again, the statistics of the world or the statistics of your own experience. Like every time I see this happen before this, oftentimes it's because this.
So sorry, but I think I'm going to push back on that. I think strong statistical dependence and causal relationship are still different from one another. I think that's something that Tim was getting at as well. And I do think that to infer the causal, to make that further jump, to make it causal, I do think we need to filter it through some semantic priors that we have acquired. And so Yeah, I think some people, the nativists, would say that we have it since very young age. I think we don't, but I don't know. Like, it's up for grabs.
So I agree that there is a difference between the statistics and causality. What I would also argue, though, is that there is also a correlation, and over time you will eventually, even though it's not always the case that A before B means A cause B, oftentimes it does, and so you have that association built in.
At the same time, we can learn causal relationships one shot. So we don't necessarily need to see it many times, which again speaks to the fact that it's something different from just an episode. It's matching some learned, acquired knowledge that.
Totally agree with that, Ida. I totally agree that whatever is being learned in your schema for objects falling off things, that kind of stuff, that thing knows about causality. But did it learn it because of some funky do algebra, or did it learn it over experience and then apply it to every new experience?
Yes. Yeah.
Right. I see what you're saying. Yeah. The filter itself have been learned through experience. I agree.
Yeah.
I guess, but nativists, like, I guess the 70s, 80s, MIT/Chomsky crowd might think that it's innate, but I think even they revised a little bit. So.
Cool. That was a great little discussion. Thank you very much, everyone. Okay, I should return to a question from the audience. And I swear to God, I did not plant this question. It is literally just the most upvoted question in the Q&A. Forgetting is almost as important as memorization. This is from Victor Roykova. Sorry, Victoria Roykova. Sorry if I mispronounced your name, Victoria. Forgetting is almost as important as memorization for memory formation. What can neuroscience offer for AI to start modeling human-like forgetting? And indeed, I'm curious to know that for those of you here who study humans, because this is not something I know about. What do we know about forgetting in human beings? So we heard from Nicole, for example, today about what we tend to remember. What is it that we tend to forget? People ask me this all the time, and I never actually have a good answer because I don't study the human literature sufficiently. So I'll start with you, Nicole, in case you have an answer to it, and if not, someone else.
Yeah.
Like, do we have any idea of which sorts of images people tend to forget?
Yeah, so in terms of this, the type of memory, just this basic processing, right? So this, for example, the memorability I was talking about. So memorability, rank order for images, it tends to maintain its rank order across minutes, hours, days, months, right? So a really robust phenomenon. We're forgetting them all at the same rate. It's not to say that we're not forgetting images, but we tend to forget them all at the same rate if you treat them all as the same. Now you can give, there are all those sorts of paradigms where you can give certain images kind of a primacy, or, you can attach them to something important. But then you're just going to remember them better initially. I don't know that there's evidence that you're going to forget them differentially. So yeah, this type of I think about the type of memory that I talk about and I study as a very tractable and almost primitive form of memory. And so I think that this question is really more interesting for the people who study like these, what I think of as the more sophisticated sorts of memory. So I'm going to punt that question to the rest of the panel.
All right. Well, in fact, Ida has written a very relevant paper to this, so let's punt it to you, Ida.
Thank you. So I have to give a shout out to a lot of people who actually do very good forgetting studies in humans. Take a look at papers from Ken Norman's lab, especially. And also, I mentioned earlier, the Anderson lab has done some work. So the kinds of work, for instance, like retrieval-induced forgetting is one, where you will remember some things that are in some distance correlated with one another, related to each other. The one that was less activated or moderately activated gets forgotten, in fact. So it's this counterintuitive finding that when you make people remember something, they can forget other things. There is a series of studies on this, on memory enhancement and forgetting. And so we modeled this in this idea of spreading activation and memory plasticity model, where the plasticity comes from this non-monotonic plasticity function that Ken Norman has shown in numerous studies over the course of 13 years before I joined his lab. And others have shown this, others had used this. There was this idea that some people had, and there was a sort of a big argument in the field of memory. One side said, we never forget anything. The only thing that happens is that some things get more activated over others. And there was another camp that was saying, actually, some things deactivate others. Sometimes we do lose memories. And so that argument, although it's not entirely resolved, I feel like it's no longer at the extreme of we don't forget anything anymore. And this idea of non-monotonic plasticity was one of the ways where, with a neural network model that was published, I think, in 2003. It's 63 pages in Psych Review, and Ken Norman is the author. He was, I think, the first model that explained these kinds of retrieval-induced forgetting effects. There are others, and those are the kinds that we are addressing here. Another thing that we showed together with Aline Coleman in two papers that were empirical, and in this paper we model it, is that when humans talk to each other in the conversation, we activate some things and deactivate some things, so we lead to retrieval-induced forgetting for each other. So if I keep talking about something too much, you might forget something that's related to it. And so we did studies in different networks of humans. Turns out combining these ideas of memory plasticity with different networks of humans talking to each other also predicted the results we found in collective memory studies. So that was nice. Some things that we haven't modeled work like the ones that the Anderson lab does, which is directed forgetting studies. And they're obviously interested in it in the context of psychiatry, for instance. So one thing about it is, if I tell you, hey, remember that thing I said? That's not true. Forget it. And they put participants in the scanner and they keep telling them to actively forget certain things that they saw before. And it turns out that the relationship or connectivity between prefrontal cortex and the hippocampus plays a very big role here, ventromedial prefrontal cortex and the hippocampus, if I remember correctly. And they found some dissociation between the lateral and medial prefrontal cortex and the hippocampus in this interaction that I think you should look at their papers. So yeah, so there is active forgetting, there is, retrieval-induced forgetting, and also there are other forms of forgetting that are necessary for plasticity because something changed. For instance, the address to my friend's house has changed. I better forget that because otherwise every now and then when I'm not thinking about it, I'm going to go to the wrong street. It has happened to me before. And especially when I'm on a bike and I'm listening to music, I'm not thinking, I just go, oh no, they have moved, so I have to move back. So yeah, so sometimes forgetting is actually useful, enables flexibility and plasticity. Sorry, I talked too much.
You didn't. That was awesome.
Yeah, it was. It's with this retrieval. It's one of the. I have nothing clever to say, by the way. I just said it all. But it is worth noting that certainly in the UK, this retrieval-induced forgetting is one of the few parts of psychology that's made it actually affected the rest of life. Because they basically stopped taking witness statements seriously in law courts now in the UK because of it. Because when they are interviewed by the police, they retrieve the memory and it changes. And so when they go back into court, the whole thing is so yeah. They're massively downweighted witness statements in UK courts.
Okay, so neuroscience has actually impacted the justice system. Now let's see if it can impact AI design on this question. So we've just got a couple of minutes left, and I feel that I would be remiss not to take another question from the audience. I guess I'll do this democratically rather than just picking my favorite one. So the second most upvoted question, which I actually am skeptical of. I'll be curious to see what the panelists say. It surprises me that in the 21st century, researchers continue to talk about memory using computational metaphors and making references only to the brain as if it were a disembodied organ. Memorizing is something we do with the whole body. That's not really a question, but maybe I'll ask all of you for your comment on this. Is memorizing actually something we do with the whole body? If we build AI without giving them bodies, are we never going to be able to capture the realities of memory for human beings? Sorry, I know I need to ask someone directly. So here, I'll start by punting that to you, Tim.
I think that when you remember something, you do remember the sensation in your whole body, and I think that's a really important thing. those sensations, there are lots of parts of your body that have neurons in them that where those sensations are can really affect your emotions. And so I think, no question, your whole body is part of the memory. But whether the computation, here's maybe the easiest part. The thing that I would say most clearly is this: out of all the organs that you could remove from your body, the one that would have the biggest impact on your memory would be the brain.
Touche.
Yep. I think that's kind of a key point, isn't it?
Yeah.
Yeah, I guess for me, yeah, that is the key point. And I think, there, as you say, there's really interesting things and ways in which memory ties into our body. But at the end of the day, the reason everyone here focuses on the brain when we're studying memory and not a fully embodied system is exactly that, probably. But okay.
But what I just write in the chat.
Yeah,
now
if anyone wants to jump in on that one last time, actually, yeah, please.
Yeah.
Go on. Sorry.
What I was going to say was that if you accept this idea that every experience is essentially integrating information from various domains, right? So whether you have a representation of a person in whatever your temporal lobe or your prefrontal cortex, or even representations of a sensation in your body or your heartbeat, or even things that evoke emotions, all of these different pieces of information are integrated together as a memory. And so clearly the inputs from your body are part of that memory, I think. And so when you retrieve those memories, you recapitulate or reinstate those patterns, which include those sensations from your body. Now, the body itself, outside of the brain, also does have memory. Like the immune system, for instance, is a form of memory, right? So, but we're, I think, talking about...
We're talking about something different, though, yeah.
Yeah.
Ida, you had something you wanted to add as well?
I just added something in the chat. There's something very interesting about this that I think we still need to properly experiment on further, which comes across a lot in PTSD and trauma literature. So during the time that I've been doing this computational psychiatry work, I've been very sort of impressed by the way they describe memories or the way they use those treatments. There are like volumes of books of that have the transcripts of therapy sessions where the patient is remembering something and then the therapist asks them. So basically you're reading somebody's course of remembering various things in these books, which is kind of a crazy thing to actually have access to. One of the things there is this idea that certain memories only get activated when the body is in a particular situation, or only get activated through the reactions that happen in the body, but you don't have consciously an access to where the memory comes from or what is getting activated or what movement activated it. And so a lot of these therapies focus on those things. And I think that that's something that is interesting. And sometimes these symptoms appear between 1 to 10 years after a traumatic event had happened. And there are very interesting studies showing that sometimes when the symptoms are very strong, the hippocampus actually shrinks. At least some of the studies have suggested this. So there seems to be some very interesting effects there that we are missing out on by not studying PTSD in a much more close way. Currently, I hope that I can sort of do some computational modeling of it, but I'm not a clinical person, so I hope clinical folks join forces with computational memory researchers to sort of study this more closely.
Great. Well, thank you so much, everyone. That was a really fantastic panel discussion, really fascinating thoughts and perspectives. And I thank also the entire audience for both being here and for their great questions. My painting is, oh God, I'm now drawing a blank on the memory for the title of it, but it's an early 20th century painting, something about Coney Island. Yeah, I forget the name now. But anyway, thank you everyone for being here. Thank you to all the panelists.
Thanks, Blake.
Ida, Nicole, Tim, and Kareem. That was absolutely fantastic, and thank you for your great talks. Hopefully next year we'll be able to actually host you here in Montreal.
Cool.
Thank you.
Fun. See you guys. Bye-bye.
Thank you, everyone. It was a pleasure.
Take care.
Okay, so that was our panel discussion, and thanks to our panelists, and thank you, Blake, for moderating it. And now Kareem just have a quick announcement to make, so let me just invite him on screen. Hey.
Great. So are we back on live? Yes, I think we are, right? Yes, perfect. So that was a fascinating panel. That was our first panel. We'll have another one tomorrow in the consciousness in brains and machines session. There will also be, it's not exactly a panel, a Q&A this afternoon after Eve Marder's keynote. There will be a Q&A with Sarah Sola. So make sure you don't miss anything of all the upcoming events, because everything is just going to be absolutely fantastic. We're ready now to go on lunch break, but I just have a few comments to make and just some information to share. First of all, I wanted to thank all the speakers from this morning's session. That was a real treat, and now we're looking forward to all the rest. I would also like to thank all the attendees. I also want to remind everybody that on the website, on main2020.org, there is a job board that we created. So if there are positions in your lab, at your university, at all levels, from internships to masters, PhDs, postdocs, and tenure track positions, please go, specifically related to neuro, AI, and the intersection between the two, please go to our website and it will take you 60 seconds to post any job or openings that are available, and they will be available to all the attendees. So many people have registered, so this is a great opportunity to share this information. So use the job board, it's on the website. The other thing I wanted to mention is GatherTown. That's our social space. It's open throughout the meeting. Just at the bottom of the screen, you'll see a green button that says GatherTown. You can just click on that, it will take you there. If you want to have your lunch break, why not have it in GatherTown? You will have a small avatar. You'll be able to control the avatar with just the arrows on the keyboard. And you can just find the place somewhere, maybe bump into some people you know, or maybe meet people you don't. And that's have your lunch break, or maybe just network. And there's also a room full of games that you can go play. So I recommend you just go and explore that. I'm just going to quickly tell you this afternoon, we have an outstanding program. We will hear talks by Alona Fish, Jan Charret, Beckett Ebbets, the keynotes at 3:30 by Eve Marder, followed by the Q&A organized by the student committee, by the student team, with Sarah Sola. So you'll be able to ask all your questions to Sarah Sola, specifically also those related to being a student or an early career researcher in the field of neuroscience and AI. So I highly recommend that. I think that's all I wanted to mention. So have a good time, enjoy this. Everything is being recorded and is also available normally through the live stream, also on YouTube at the same time, and will also be available for replay after actually not even after the meeting. Each time we finish a session, that session is available for replay. So you can actually basically go in on the upper left corner of the screen, it says schedule. You can just click there and you'll see all the different sessions, and you can just pick whichever one you want to watch and you can watch it again. It's already available. Okay, also follow us on our Twitter account for the main community, also for the Unique Center, and have a good lunch break or a dinner break or whatever break you're having in whichever part of the world you are. Again, we're really happy to have people and attendees from over 60 countries attending this meeting and over 2,200 people that have registered. So thank you so much, and have a good break. And we'll be back Montreal time, 1:20. Okay, that's 1:20, and our chair this afternoon will be Guillaume Lajoie. Okay, so see you.